nanohub.org.
So today I wanted to end up the discussion about this frequency modulated AFM by showing a few results from the literature that kind of describes the capabilities of this technique, allows you to compare it to what you can achieve with amplitude modulated AFM. So I think the way I like to motivate the lecture is to discuss the history behind seeing atoms with an atomic force microscope. If you recall the discussions we had with the scanning telling microscope, from the very early days of STM, atoms were observed. It was not a problem. It was not anticipated, but once the images started to come in, and then models were developed that allowed an understanding of how this front atom on an STM tip, when rastered over a substrate, can give rise to an image with atomic resolution. So the question is, can you see something similar? Can you trace the history of atomic resolution in AFM in a similar manner? And if you go back and recall the history, the first paper on AFM came out in 1986. The first paper that reported atomic resolution with an AFM came out in 1987. This was a paper by Binnig and his co-workers. And what they did is they imaged a graphite surface, a highly oriented pyrolytic graphite surface with an AFM tip in contact mode. And they produced an image which showed periodicity, which reflected the position of atoms in the substrate. So is AFM capable of atomic resolution? The early history of the subject says yes, right, very early on. But that was contact mode scanning. The frequency modulation method was proposed in 1991 by Albrecht and his co-workers. And between 1991 and 1995, various groups tried to implement this frequency modulated AFM. They tried to use it to image atoms on surfaces without a whole lot of success until the year 1995. 1995 was a breakthrough year. I can find, at least my reading of the literature, I can find about 4 or 5 papers in 95. This paper by Luthi that was published in early 1996 could just as well be above that red line. It just so happens it came out in 96 rather than 95. There were about 4 or 5 seminal papers in the 1995 time frame which indicated that atomic resolution and frequency modulated AFM could be achieved. The first international workshop on non-contact AFM, on this frequency modulated AFM, followed a few years afterwards. So in 1998, that was the first conference devoted to the FM-AFM community. Now I think we're in the 13th or 14th year of that conference, and it's a conference that meets once a year, just devoted to the FM technique primarily. And then finally in 2002, there was this very nice book that came out about non-contact AFM, which is basically frequency modulation AFM. So this FM-AFM has sort of followed a completely different route than the amplitude modulated AFM that we discussed earlier on in the semester. The atomic periodicity that you can see in contact mode AFM is demonstrated in this sequence of images. This is data that one of my students, Dave Schaefer, took when he was a PhD student here back at Purdue in the early 1990s. He used contact mode AFM to image the surface of mica, and on a good day, he was able to obtain images that are, I copied from his thesis. I put up here just so you could see. This is an image that's taken by literally rastering a tip across a mica substrate at a very rapid rate. There's clearly a modulation in height of the image as the tip scans across the surface. The periodicity of that image can be matched very nicely to the known crystallographic structure of mica. So if you go and you make measurements of the spacing between bright spots in the AFM images, you'll find that you can match them up pretty closely with the known dimensions of a mica substrate. The images scale with scan size, right? If you go to bigger scan size, you see more atoms, more closely packed, right? If you rotated the image, you could see that the periodicity of the atoms rotated. So we think it's a legitimate image. It's not an artifact. We were not able to identify the atoms that were being imaged in this early stage of AFM. So we saw a periodicity that matches the periodicity of mica, but we could not identify whether we were imaging, let's say, the silicon or the aluminum atoms that are known to exist on a mica surface. And we were not alone in being able to achieve this. Many groups throughout the world saw atomic resolution in contact mode scanning. But there were a number of issues that were raised by these contact mode scans, and I'd like to just run through those to give you a sense of the skepticism that you need to have when you do atomic force microscopy. The first thing that many different groups throughout the world recognized was that these contact mode images required a rather large normal force in order to see the atomic periodicity. So you had to really push the tip down hard onto the substrate. Now, what's the consequence of that? Well, the consequence of that is, if you go back to the lectures that we gave on contact mechanics at the beginning of the semester, anytime you push a tip up against the substrate with a significant amount of force, a contact radius is going to develop. So, for instance, if you, let's say, take a Hertz model, right, you can calculate the contact radius that develops between, let's say, a spherical tip. Tip radius could be 20 or 30 nanometers. Right? You could calculate the contact radius that forms between the apex of the tip and the flat surface just due to contact mechanics, given the applied forces that you need to produce these images. And what you find from that back of the envelope calculation is that these contact radii could be on the order of 2 nanometers, which means that there's a rather large region of the tip in very close contact with the substrate. In this case, let's say it's a mica substrate, okay? So that means that the surface area in contact with the mica substrate is much, much greater than the unit cell area of the atoms that we're trying to image. So if A naught is the spacing between atoms in your substrate, and you just form the ratio of the contact area to the area of atoms in a unit cell, you'll find that number is greater than 1, right? So how can it be, how can you see individual atoms, right, if you're sliding a big area of the tip across a substrate? You know, you don't have this leading atom, this front atom idea that you have in STM. That doesn't work here because the forces that you're applying are rather large. The other obvious concern is these large normal forces imply that there's going to be a rather large frictional force. And so as the tip is slid over the substrate, right, the tip will tend to twist, or the cantilever will tend to twist by any frictional forces that are in the lateral direction that are exerted by this large normal force. And so then you have to worry about how is the twist of the cantilever, is that really an orthogonal motion compared to the up and down motion of the cantilever? Because if there's any coupling between the twist in the cantilever and the up and down motion of the cantilever, then you might get confused. Your feedback circuit might get confused because what the cantilever really does could be twist, and yet it could generate a signal that would indicate that the cantilever goes up or down, just depending on the size of the friction. So that's a puzzle. That's a problem that you have to sort out if you really want to believe these are images of atoms. And then lastly, the thing that really captured everybody's attention was the fact that when you were able to see atoms in contact mode AFM, you never saw defects. You never saw an atom missing from the lattice. All the atoms in the lattice were filled. And you would think somewhere, sometime, somebody would find a surface where one or two atoms happened to be missing from their official lattice sites. And so therefore, instead of seeing a periodicity of atoms over a region of the scan, maybe there would be a hole that would be represented by this defect. So that was a puzzle. Where are the defects? Why don't you see defects in these images, these contact mode images? So a paper was published in '96 by Morita and co-workers, where they investigated this a little bit more in detail, and they pointed out that perhaps the images that appear to have atomic resolution, perhaps those images are related to a stick-slip friction mechanism. The stick-slip friction goes like this, okay? It's like, okay, there's a single atom on the end of the tip, there's a group of atoms on the substrate. Maybe the friction between that lead atom on the tip and the atoms on the surface, right? Maybe that friction is highest when the atom on the tip is directly over an atom in the substrate. And maybe that friction force causes the tip to stick whenever the two atoms, the dark atom at the apex of the tip lines up with an atom in the substrate. So maybe there's a stick mechanism. And then as you continue to raster the tip across the substrate, all of a sudden the tip suddenly slips and goes to the next atom where it gets stuck again. Okay? Now, if this mechanism is in place, you would then see some sort of a periodic modulation of your image, which has atomic resolution, because the atom is getting stuck every time you translate the tip through a distance A. A is the separation between the atoms and the substrate. So you would see a periodic modulation of the tip as you move the tip across the substrate, but you would in no way call it an imaging process, because the tip is literally slipping between atoms, right? You're not actually imaging the space between atoms. You're just causing the tip to slip from one atom to the next, and that causes a perturbation in the motion of your cantilever, which your software interprets as a bright spot, which you then interpret as an atom. So this is an objection that's based on the friction argument. The fact that we're applying a large normal force, that implies that we've got a large frictional force, right? And it's hard to argue against that, because of course that mechanism has been investigated and proved to be true in a number of situations. People have looked at this carefully since then. The other argument that came out in Morita's paper was this idea that isn't it strange that all the atomic images of contact mode AFM, all those images were obtained on these layered materials. These layered materials are like highly oriented pyrolytic graphite, mica. We did this in molybdenum disulfide very early on, and again, molybdenum disulfide is a layered material. So Morita raised the issue, well, what happens if, let's say, a small flake of this layered material happens to get stuck to the apex of the tip? And I illustrate this. This is a picture from his paper, right? Then as you move the cantilever across the substrate, you're actually moving that entire flake with respect to the substrate, let's say. And of course the flake, right, has atoms in it just like the substrate does. So you could imagine that there's going to be, let's say, a stick-slip mechanism between all the atoms in the flake with the atoms that are underneath it in the substrate. And so then as you scan the tip over the substrate, right, what you're really seeing is you're seeing an image that's related to how that flake slides across the substrate. And since the flake's got the same atomic periodicity as the substrate, it wouldn't be surprising that there's a modulation of the tip position as the flake moves across the substrate. And that modulation in the tip position in no way has anything to do with your ability to image an individual atom. It's just telling you something about how the flake slides across the substrate. Now that mechanism is very nice because it allows you immediately to see why there's no defects observed in a contact mode AFM, right? If there happens to be an atom missing in the substrate and you're really sliding a tiny flake over that region of the substrate, you're not going to see the defect because what you're imaging is going to be related to the lateral dimensions of the flake, not the lateral dimensions of the tip interacting with the substrate. So a defect in the surface layer of the substrate would not be observed experimentally, which of course matches what most of the experiments were showing. So it was argued that perhaps this mechanism here of this so-called cleaved flake might be the real explanation for the atomic images that were attained in contact mode AFM. So I hope you get a sense from this discussion that when you do AFM, you really never know what's really going on between the tip and the substrate. You can't go in there and look with any great detail. You can't look with high resolution to see exactly what's going on. You have a picture in your mind, right? And often that picture in your mind is translated to nice flashy images in PowerPoint. Right? But there's no guarantee that the images in PowerPoint that you create accurately reproduces the physics that goes on between the tip and the substrate. So you have to be very skeptical in this business if you really want to interpret your images correctly. You have to worry about all these issues, and you have to do sidebar experiments to convince yourself that you're really imaging what you think you are. Okay? So, are there any reports in the literature that you can find which show atoms with an amplitude modulated AFM? And the answer to that question is it's pretty hard to find those images. One paper I like is the one that I reference here in 1997. This was an atomic resolution image of a silicon 111 surface. Okay, and it was performed in a constant amplitude mode of scanning. Note that the amplitude of the tip here is 0.8 nanometers, so it's about 8 angstroms. So the tip motion here was very small compared to what you can achieve today. The Q factor of the cantilever was reasonably high. It was on the order of 500. But I think it's pretty clear that if you look at that picture, especially if you take your glasses off and look at that picture, you can start to see a periodicity that mimics the known reconstruction of the silicon 111 surface. The silicon 111 surface has this very complicated reconstruction that we talked about way back at the beginning of the semester. That's evident in this image. Furthermore, from this image, you can see there are defects, there are holes, there are black spots which indicate atoms are not there. So this is one of the few examples of an AM/AFM image with atomic resolution. And there's really not a whole lot of reports from the 1990s that report this. And the question is why? I mean, something clearly is going on here because, AFM is done virtually every university in the world, right? So there's thousands of people doing AFM every day. You would think if people would see atomically resolved images in AM, AFM, they would be published in great number and a lot of fanfare, but they're not. There's not really that many out there. Why do people use FM, AFM, right? The feeling was that if you use this FM, AFM technique, you can focus on sharpening the resonance of the cantilever. So typical micro cantilevers that you buy and run in air have Q factors between 100 and 500. Q factors that you can obtain with these tuning forks can be on the order of 20, 30,000 in an ultra-high vacuum. So the sharpness of the resonance goes way up when you use a tuning fork AFM. And the feeling was that if the sharpness of the resonance goes way up, then it's much easier to measure a small frequency shift. Now, the frequency shift, of course, is going to come about when the tip starts to interact with the substrate, this complicated interaction potential that we discussed about 2 lectures ago. Right? The frequency shifts can be small, fractions of a percent, so you have to be able to track that accurately. And the feeling was that this frequency modulated AFM with a high Q factor cantilever with a high Q factor, is capable of doing that, so that you could, with the phase lock loop technology, right, you could accurately track the position of the resonance as you scan the tip across the substrate, and you could use that frequency shift then to interpret, you could use the frequency shift to infer the topography, right? So as the tip moves further away from the substrate, frequency shift is small. As the tip gets closer to the substrate, the frequency shift gets large. If you build a feedback loop that keeps the frequency shift fixed as you scan over the substrate, then you're going to be constantly moving your substrate up and down to maintain that constant frequency shift. And in the process of moving that substrate up and down to maintain constant frequency, you're going to get an image. You're going to get a topographic image of the substrate. So that's called constant frequency imaging, right? Basically keeping the frequency, your feedback loop is keeping the frequency of the AFM cantilever fixed as you scan across the substrate. So Giespel was a pioneer using this tuning fork AFM, and this is a picture that he published in 1995. Started to turn the tide of atomic resolution images with AFM. He was scanning a silicon 111 surface, 7x7 reconstructed. He was taking an image. Most of the image is indistinct. I mean, there's nothing spectacular about most of the image. It looks like there's a fog spread out over the substrate. You know, it's featureless, right? It's featureless. But then all of a sudden, for about a half a dozen lines or so, for whatever reason, he was able to achieve line scans in which the position of the atoms in the silicon 111 surface were clearly resolved. And then that capability disappeared again after a half dozen lines. But that very sharp, distinct region of the image where you can clearly resolve the atoms, that was sufficient to generate a science paper in 1995 claiming that this frequency modulated AFM is the technique to use if you want to use AFM to image atoms on insulating surfaces. So it was a big breakthrough, and it's remarkable because it's just a few line scans where everything worked. So what happened between the first row of the clear image and the bottom row of the clear image? What actually happened? I mean, why did the image degrade again? It's hard to say. You know, probably the tip atom, the lead tip atom on the surface, on the tip, probably got moved or damaged. And in the process of getting moved or damaged, then the image went back to this indistinct featureless image that you see. But for those few line scans, things work very well. Giespool was not the only one to achieve atomic resolution in 1995. I also pick out a paper from Morita's lab, published in the same year. They were investigating the indium phosphide 110 surface with FM, AFM. And they published this image where they were clearly able to see the position of atoms on the surface of the substrate. But most notably, they found a region of the substrate where there were no atoms present, where there was actually a defect. So this image, in my mind, convinced a lot of people that this FM, AFM technique was really capable of atomic resolution. That when you started to see the presence of defects in the surface, you could no longer make arguments based on friction or flakes of material sliding one over the other, right? This was truly an AFM tip imaging a substrate with a resolution that's approaching lattice constant of the substrate. So the resolution here is probably a few hundred picometers. It's the only way you can see, right? It's the only way you could see these individual atoms, and the only way you can understand why there's actually a defect that's imaged. Again, very careful work has been done to investigate this further. I just wanted to show you some nice data again out of Morita's lab. This was published in 2000. I think this is a gallium arsenide substrate. Yeah, it is. It's a gallium arsenide 001 substrate. The images were obtained in ultra-high vacuum. This is obtained using the FM, AFM technique. And there are 3 images of the same region of the substrate. The difference between these 3 images is that the minimum separation between the tip and the substrate has been adjusted. So as you recall, the substrate is here, the tip is positioned at some point, then you cause the tip to oscillate back and forth. And if you use Sater's algorithm to interpret the frequency shift of the tip, right? The frequency shift of the tip is related to the tip sample force at the point of closest approach of the tip to the substrate. So if you have the tip out here and you obtain an image of the substrate with a motion like this, or a motion that more resembles this, right? In principle, you're going to get 2 different images of the substrate. The question is, which one is better? And so that's what this paper investigates. These are constant frequency images, which means that the frequency shift is held fixed as the substrate is scanned underneath the tip. So the frequency of the cantilever is about 150 kilohertz. The constant frequency shift obtained for each image is indicated on top of the image. So there's a 31 hertz shift, a 62 hertz shift, and a 70 hertz shift. But the important parameter that distinguishes these 3 images is this parameter d min, which describes how close the tip is getting to the substrate for the 3 separate images. So it's not the frequency shift being held constant that determines the resolution of these 3 images. It's this minimum separation that's been achieved. So in the first image, the minimum separation between tip and substrate is held fixed at about 0.4 nanometers. That's 4 angstroms. Then it drops down to 1 angstrom. Then it drops down to 0.8 of an angstrom. And I think you can clearly see that the ability to image the individual atoms on the gallium arsenide substrate, that ability increases, gets much better as the tip is brought into close contact with the substrate. Now this is all being done with a tip motion, with an amplitude of the tip motion that's 9 nanometers, so that's about 90 angstroms. So the tip motion is swinging 90 angstroms back and forth about some reference position. And all we're doing is we're just adjusting the point of closest contact, right, to obtain these images. It's a really nice study, and it shows the importance of getting the tip close to the substrate. You can't see the individual atoms when the tip is about 3-4 angstroms away from the substrate. That's the image on the left. But as the tip comes in closer and closer, it starts to get on the order of 1 angstrom away from the substrate without touching, right? Without touching, because we're still in this potential well. Right? We're not really in the repulsive regime here yet. Right? You can start to clearly resolve the atoms. So it's a very nice study. Notice also the high Q of this circuit. This cantilever, it's 38,000. Right? Very high compared to cantilevers that operate in air that are normally used in this AFM mode, the amplitude modulation mode. Well, there have been a large number of studies published now using frequency modulated AFM. Investigators have looked at surfaces other than gallium arsenide, silicon, mica. Just wanted to show you, here's an example of imaging DNA with the frequency modulated AFM. This was published 10 years ago. And if you look at that image carefully enough, you might be able to convince yourself that you actually see a twist, a helical twist in the DNA that's been imaged by the frequency modulation technique. So the claim is that this is a double-stranded piece of DNA. So there's 2 strands that are twined, one with respect to the other. And of course, it's well established that those 2 strands are twisted in a helical fashion. And the image suggests that, actually. If you didn't know that the strands were twisted, you might be able to look at that image and infer that they must be twisted, okay, to produce an image that appears this way. So it's just another indication of the resolution that's possible with frequency modulated AFM. I also wanted to mention a study, again, performed in Giespel's lab in 2000, where he imaged the silicon 111 substrate. Again, that's the that's a substrate of choice for many FM AFMers, because the position of the atoms is so well understood. You can see very clearly the quality of the image now that's being obtained. You can also clearly see there's a defect in the upper left region of that image, which indicates that some atoms are not in their official lattice positions. So that tells you that you really are imaging atoms with the tip. And the point that Giespel pointed, or the feature of this image that Giespel pointed out, was that if you look at each atom, it has a modulation associated with it. And that modulation appears as 2 crescents, right? He calls them crescents. I show an enlarged image of one atom that I copied from his paper. And you can clearly see that the atoms appear to have a modulation associated with them. And that modulation is subatomic. It's a modulation of the position of the height of the individual atom. It's not a modulation of the space between atoms. And then you have to ask yourself the question, what could that modulation be due to? So I think you have 2 choices. One choice is you say it's an artifact, which could well be. The other choice is you take that modulation seriously, and then you start to imagine what could produce that modulation. So I believe this image was taken with a tungsten tip, and Giespel goes through an analysis in his paper where he argues that this modulation that's observed on the top of one atom is actually due to different electron orbitals that are protruding from the front atom of this tip. And the orientation of these different orbitals when they interact with the tip is sufficient to produce this very small modulation in the height of a silicon atom as its image. So I think this is still a controversial interpretation of the image. There are many people that believe that that's an artifact. But nonetheless, it's still remarkable that, and I think it's still an open question. I don't think it's been clearly resolved, whether or not these orbitals of the front atom on a tip are capable of imaging atoms in a substrate with some subatomic resolution. But nonetheless, it's an indication of the sensitivity of the FM-AFM technique. It suggests that with further improvements, you might actually be able to image atomic orbitals as they interact one with another using very carefully constructed pieces of equipment that are very stable. So I like it because of the vision that the image suggests. It shows you there's still a lot of work to do, I think, with the frequency modulated AFM technique. I like to switch gears now away from images and talk about force spectroscopy, because in my mind, one of the most interesting features of this frequency modulated AFM is that it allows you, just by measuring a frequency shift as you move the tip closer to the substrate, it allows you to interpret that frequency shift in terms of a tip sample force. And that opens up all kinds of interesting possibilities, and one of the possibilities is indicated in this paper published in 2001 by Lance and co-workers. What they did was I think they were imaging silicon 111. I think that's a silicon 111 surface. They were imaging the surface, and they did force spectroscopy curves when the tip was positioned over individual atoms. So the individual atoms that they investigated are labeled 1, 2, and 3 in the image. 2 and 3 are clearly atoms. 1 looks to be a hole. It looks to be like a hole between 6 adjacent silicon atoms. And what you might expect that the force versus distance curve obtained when the tip is positioned over 0.1, you might expect that to be different than the frequency versus sample displacement curve obtained when the tip is positioned over atoms 2 and 3. And so if you read their paper, they start to present these frequency shifts as a function of sample displacement for tips positioned over different atoms. And there does seem to be a slight difference between the force distance curve, or the frequency shift versus sample displacement curve. It seems to be a slight difference between curve 1, which is in blue, and curves 2 and 3, which are in green and red. And the great thing, of course, is you can take that frequency shift and interpret it in terms of an interaction force. And that's what they've done. They've converted the frequency shifts to forces. And sure enough, what they find is that there are different tip sample forces depending on where the tip is positioned. And of course, this is something that you would expect if you just sit down and think about it, but this was one of the first demonstrations, I believe, that the frequency modulated AFM had the capability of measuring difference in forces between an atom on the tip, which presumably is protruding from the bulk portion of the tip, and different atoms on the substrate. So that's a very nice idea. I wanted to show you how that idea has evolved, just to give you a sense of what you can do with this frequency modulated AFM. And I wanted to do that by introducing these 2D binary surface alloys. This is a topic that it's captured a lot of interest. And basically what happens here is you can take some atoms in the periodic table and you can exchange those atoms with substrate atoms in a very easy way, just by heating the surface of a substrate up. So of all the atoms in the periodic table, these 2D binary alloys tend to focus on the elements that are enclosed by that black rectangular box. And not surprisingly, it involves a silicon substrate, and it involves germanium, tin, and lead atoms that are then added onto the silicon substrate. The silicon substrate is heated up, and in the process of heating, the added atoms of germanium, tin, or lead can mix in with the surface layers of the silicon atoms, producing a binary alloy, binary surface that is now comprised of silicon germanium, silicon tin, silicon lead, depending on your choice of add atoms. Now, why would you want to do that, right? Well, first of all, it's interesting that you can do it. This alloying, the surface alloying is kind of an interesting effect. But it produces new surface structures, and I'll try to make that clear in the next few slides. So part of the problem that you have in making electronic devices is you're kind of stuck with the material that you're given. You can't twist a knob to adjust the lattice constants, let's say, of the silicon atoms on silicon 111. You just can't do it. That's fixed. But these binary alloys, by mixing in small amounts of germanium, tin, or lead, right, allows you to make subtle changes in the rearrangement of the surface atoms. And those subtle rearrangements in the position of the surface atoms could and do cause the local surface electronic structure of the material to change. So if you're just interested in modifying, let's say, the surface electronic properties of a material, again, you don't have a knob that you can twist to do that, but by carefully alloying in different atoms, right, you might be able to subtly move the surface structure, the electronic properties of the surface around, tailor them to a particular need. So it gives you some additional flexibility in maybe device design and fabrication. So that's the reason that this system is of such interest. It goes under the name 2D binary alloys, and if you go to material science conferences, usually there's a whole session that's devoted to studies based on add atoms of germanium, tin, or lead onto silicon surfaces, and then reports about what happens. So that's the motivation for behind this work. Just want to illustrate the type of images that you can obtain when you, in this case, we're taking a silicon 111 substrate. Tin atoms are being evaporated on it. Very sparse amounts of tin atoms are being evaporated. After the evaporation, the substrate is heated up to a certain temperature and then cooled back down. And then the surface is imaged with frequency modulated AFM. So frequency modulated AFM is capable of atomic resolution, and that's what you see in these images. What you find is that if you put a sixth of a monolayer of tin on a surface, heat it up, cool it back down, the surface appears as shown on the far left panel of this image. And if you actually sit down and count the number of bright atoms versus the number of dark atoms, you'll find that it's about a 50-50 mix of tin and silicon. And as you increase the tin coverage, so you go to a quarter of a monolayer or a third of a monolayer, what you find is that the coverage of the tin increases, as indicated by the predominance of bright spots in the image. You find that the images of the silicon atoms goes down. There's fewer and fewer of them. And so by the time you get about a third of a monolayer of tin deposited on the silicon 111 surface, you'll find that the surface is now 99% tin, about 1% silicon, which is the far image on this slide. So there's two things I want to comment about that image. Well, first thing I want to comment about that image is if you measure the position between the bright spots are the tin atoms, the separation between the tin atoms is about 3 times the separation between the silicon atoms on a pristine silicon 111 surface. So in the process of forming this surface alloy, you've produced now a tin-rich surface on silicon, and the lattice constant of the tin atoms is considerably greater than the silicon atoms that you would find on a pristine silicon 111 surface. So that's a useful thing to be able to achieve. And the other thing that you notice from this image is that the silicon atoms appear as defects. They are actually, in the FM, AFM images, they're down. They're dark, right? Which means that they're at a lower Z position with respect to the surrounding tin. And the question is, why do these silicon atoms look like they're down? Why do they look like they're defects? They're pushed into the substrate. And that can be understood in detail by the way the difference between a silicon atom binds to a silicon substrate and a tin atom binds to a silicon substrate. And it turns out that when a silicon atom binds to a silicon substrate, there's an unpaired orbital that protrudes above the silicon atom, and the net result is that there's an increased force on that silicon atom by the silicon substrate. So the silicon atom is actually sucked down onto the substrate. Whereas when you put the tin atom on, the bonding is different, and the tin atom no longer has that unpaired orbital. It's now filled, and it appears in the images to be at a higher position. So it's a detail, but it's an important detail that allows you to understand in great detail why that image of tin on silicon shows silicon atoms as being depressed. Right? It's due to the details and the bonding between these atoms on substrates. So it's just an illustration of the type of information that you can back out from these images. Once you have the image, then you can start to try and understand the features that you see, and you get some insight into what's going on at the atomic level. The reason I want to talk about this system is because now you've got a system where you've got two different atoms that are very clearly distinguishable on a substrate. Very clearly you can see where tin atoms are, very clearly you can see where silicon atoms are. So why not put the tip above a tin atom and do a force spectroscopy measurement? Take the same tip, put it above a silicon atom, do a force spectroscopy measurement, and see if there's a difference between the interaction force of that tip with a tin atom and a silicon atom. So if you think about it, this is perfect, right? This is an ideal experiment because you really get some fundamental information out about interaction forces. And that's what was done. That's what precisely was done in this 2006 paper in Physical Review B. When the tip is positioned over a silicon atom, you measure the frequency shifts as a function of Z. You use Sater's formula to take those frequency shifts to give you the force between the tip and the surface. Between the tip and the surface, you want to measure that tip sample force. That's what's plotted on the right panel. In the red curve, if you position the tip over a tin atom and you do the same measurement, you get the black curve in this data panel. And you can see there's a clear difference between the two, right? It looks like when the tip is over the silicon atom, for whatever reason, the attractive force between the tip and the silicon atom is greater because the depth of that tip sample interaction force, the depth of that is about a nanonewton greater when the tip is over silicon compared to over tin. And then also you can see that there looks to be a slight difference in the width of the interaction force, right? It appears that when the tip is over the tin atom, the tin atom is perhaps has a shorter range force than when the tip is over a silicon atom, right? So there's important differences, and it suggests, again, right? The motivation behind this work is that you can tell something about the chemical nature of an atom just by measuring the interaction force between that atom and the tip. Right? So you can imagine if you have a dictionary of forces, shapes of forces between tip atoms and different atoms in a substrate, you measure the interaction force between a tip and a substrate atom, right? You can then look up in this dictionary what the shape of that force is, and then therefore identify the chemical nature of the atom on the substrate just by measuring the tip sample interaction force. Now we're not there yet, right? You can't do that on a routine basis, but it suggests that is a possibility. And that's very intriguing, right? This idea was pursued, again in 2007. The system was a tin-silicon binary alloy, so it was very clear which atoms were tin. It was very clear which atoms were silicon. In this study, the interaction force was measured when the tip was positioned over a variety of different silicon atoms and over a variety of different tin atoms. And the hope was that those forces would be distinctly different between the tin and the silicon. That was the hope. And the data is plotted in the upper panel, upper left-hand panel of this slide. And you can see the data overlaps one another in a quite uncharacteristic way, right? So when the tip is over a silicon atom, the force versus distance curve is plotted as an open symbol. When the tip is over a tin atom, the force versus distance curve is plotted as a solid symbol. And if you look at that upper left-hand panel, right, it looks like everything's jumbled up. There's nothing clear that jumps out at you that would allow you to say, oh, the difference between a tin atom and the tip and the force between a silicon atom and the tip, those are distinctly different. And the question is, why is that? And the answer is probably due to the fact that the front atom on the tip is getting slightly rearranged as you move the tip across the substrate and acquire these curves. So the picture that you have in mind is not a macroscopic tip that can be modeled as a sphere, and you can use DMT or Hertz models to model how the tip interacts with the substrate. That's not the correct model to understand this. The correct model to understand this data is a front atom on the tip interacting with atoms on the substrate in a very controlled and precise way. And if the front atom on that tip gets rearranged, gets moved, gets bumped a little bit between different data scans, right, you're not going to get the same result again. So that's the explanation put forth to explain why all those curves are jumbled up and mixed up. But what was discussed in this paper published in 2007 is if you just take the minimum force, in other words, the biggest force, the biggest attractive force, if you just normalize that biggest attractive force to unity, right? So for instance, you just say that the force that you measure divided by this, by some silicon set point force that's determined by a minimum force, right? If you just plot this normalized force versus distance curve, then all of a sudden this jumbled sequence of data splits out very nicely into two well resolved sets of force versus distance curves, and that's shown in the bottom left-hand panel of this slide. So notice the z-axis here, this distance axis is now in angstroms. It's not in nanometers. So this is tenths of nanometers. And there seems to be a very clear distinction between the normalized force versus distance curve when the tip is over a silicon atom versus when the tip is over a tin atom, right? Just by doing this normalization. So this normalization essentially takes out this subtle rearrangement of the front atom of the tip. It's a way to correct for that. And if you correct for that, the first approximation, the claim is you can start to make sense of these data curves. So the net result of that is that you can repeat that procedure for, let's say, a binary tin, alloy on silicon. And this is work out of Morita's lab in Japan, where they've actually performed these force versus distance curves over different atoms in a tin, lead, silicon binary alloy. And what they find is, they find that the interaction force when the tip is over a lead atom has one characteristic shape. When the tip is over a tin atom, it has another characteristic shape. And when the tip is over a silicon atom, again, there's a characteristic shape that's different from the other two. And so just by measuring first you have to obtain an atomically resolved image of this binary surface. Right? Then you have to measure force versus distance curve over each atom in the image. And you have to hope that the image hasn't drifted significantly in the course of that experiment. Then you have to interpret the data to find out what the normalized shape of the force versus distance curve is. And at the end of the day, you can then go back and say that, based on our work, right, this is a silicon atom, this is a tin atom, this is a lead atom. So you can actually start to color in the atoms by their chemical force versus distance curve. You're now in a position where you can identify with some confidence the chemical nature of each atom on the surface. So my friends from the high resolution transmission electron microscopy end of things tell me this is also possible using high resolution TEM. But they also tell me that you require heavier elements in order to make this work for high resolution TEM. So in high resolution TEM, you're basically looking at how the electron beam diffracts around individual atoms. And that diffraction is, of course, going to be determined by the interaction of that electron with the atom electrostatic core. And so apparently you can achieve this type of chemical identification atom by atom in high resolution TEM, but as I understand it, you can only do that for heavier elements. Here it was achieved for the first time on a silicon surface with 2 or 3 different types of atoms added in. So I think that's a really nice demonstration of the capabilities that this FM, AFM technique has. And it kind of indicates why this work tends to be done more in academia than in industry, because it requires many years to build up a system and acquire the techniques that allow you to interpret this type of an image. But it's still a very nice demonstration of capability. So I want to end this lecture by saying that things are starting to change. Right? This FM, AFM capability is quite remarkable, but in the last few years or so, there are studies that are coming out which indicate that if you do AM, AFM carefully, you can also achieve atomic resolution. The suggestion is that this atomic resolution is easier to achieve if the tip is positioned or is submerged under a liquid. And so the literature is not, right, the full story is not out there yet, so I don't know what the answer to the question is going to be. But I will tell you that the knee-jerk reaction, if you ask the average AFMer on the street, why is this FM, AFM technique capable of producing such remarkable images? The knee-jerk reaction would be, well, it's because of the very high Q factor that can be obtained by the cantilever as it oscillates. And that very high Q factor allows you to measure very small frequency shifts with great accuracy, and so therefore you can see atoms much easier. That explanation doesn't hold up so much anymore because in 2005, Fukama and his co-workers produced some remarkable images of a mica surface when the cantilever was submersed under a liquid, under water. So when you put a cantilever in water, the Q factor drops dramatically. Q factor could be 30,000 when the cantilever is operating in vacuum. When you put the cantilever underwater, the Q factor is 10, 20, or less, right? So if this frequency modulated AFM requires a very high Q in order to achieve atomic resolution, you would say that there's no way you can achieve atomic resolution when you put the cantilever under a liquid because the Q factor drops by factors of 1,000. But Fukama and co-workers took a mica surface and they produced this remarkable image. So this is frequency modulation of a mica surface underwater. The Q factor is about 20. The amplitude, the distinguishing feature of this is that the amplitude of oscillation is very small. So we're talking just a fraction of a nanometer. So the tip is just oscillating a fraction of a nanometer above the surface. And the amplitude of the tip oscillation is also a fraction of a nanometer. But they clearly see a periodicity that's related to the atoms on the mica surface. If you stare at this image, you'll find regions where there appear to be small defects. So I think it's a real image of a surface. We think the tip is really imaging the mica surface. But it just demonstrates that the high Q factor is not the sole determining reason why frequency modulated AFM is capable of imaging atoms on surfaces. So this is an evolving story. If we teach this course next semester, we'll probably have a different spin. We'll know more about this at that time, and probably the lecture will end in a slightly different note. But this is kind of where we're at today. So just tell you it's a continuing story that's interesting. So I think that's the end of what I have to say. All right. I'll be happy to answer any questions that you might have. Otherwise, if you come back on Tuesday, we'll talk about electrostatic force microscopy and how AFMs can be used to map out electrostatic properties of surfaces. We'll go through the techniques involved and show you some simple experiments that we've done to pull this off. So thanks for coming, and we'll see you next week. And if there's any obvious questions, I'll be happy to try and answer them. Okay, great.